Alright, this is video 1 from section 15.9. In this video I'm going to do some problems involving buffers. Alright, we are asked to calculate the pH of this mixture. It's never a bad idea when dealing with acid-base problems to list the major species. HNO2 is a weak acid, so it stays combined as a major species, but sodium nitrite, NaNO2, that is a soluble ionic compound because we have sodium, so that one's actually going to dissociate into its ions. Now, HNO2 is a weak acid, and the substance it forms when it acts as an acid is NO2-, and that's its conjugate base. So anytime you have a weak acid and its conjugate base in the same solution, you have a buffer. And when you have a buffer, you can find the pH of it by doing an ice table for the dissociation, just like before, but there's a shortcut you can use called the Henderson-Hasselbalch equation. If all you need to find is the pH, you can just go ahead and use the Henderson-Hasselbalch equation to find the pH, but this only works for buffers. So the Henderson-Hasselbalch equation is equal to, or the pH of a buffer is equal to the pKa of the acid. So, pH is negative log of H plus, pKa is negative log of Ka, plus log, and the way this is written in your AP exam equation sheet is A negative over HA, which is just the molarity of your base divided by your molarity of your acid. So it doesn't matter, what the base is and what the acid is, as long as they're conjugates of each other. You can always put the base over the acid. And what this really is would be if you did the ice table for HNO2 in equilibrium with H plus NO2-, and you had your initial concentration of H and your initial concentration of NO2, and then you did the thing where you assumed that the equilibrium, like 1 minus x or 1 plus x, was just equivalent to 1, or the idea that the minus x part of the molarity is, you can assume it goes away. That's how you end up with all of this. So it's not like a made up thing, it's just a shortcut to doing the ice table since it always works out the same. Anyway, the pKa is going to be the negative log of the Ka of the acid. So we'd have to look up the Ka of HNO2, which is equal to 4.0 times 10 to the negative 4th. All right, so the negative log of that is the pKa. So you can just figure P means the negative log of something, whether it's pH, pOH, pKa, it's just the negative log of it. So P, the negative log of 4 times 10 to the negative 4th equals 3.4. So that is the pKa of HNO2. So the pH of this buffered solution is going to be equal to the pKa of the acid in the buffer, so 3.40, we just figured that out, plus the log of the ratio of the base concentration to the acid concentration. Our base is NO2-, which comes from NaNO2, and because there's 1 mole of NO2 ions in every 1 mole of NaNO2, then the molarity of NaNO2 is equal to the molarity of NO2. So that nitrite ion molarity is 1, and then our acid molarity is also 1. So base was 1 molar, acid is 1 molar. 1 over 1 is 1, the log of 1 is 0, so in this case the pH is just equal to 3.4. And that's the pH of our buffer, and also it just brings me to another point here. Anytime you have a buffer where the molarities of the base and the acid are equal, then you're always going to have this factor be equal to the log of 1, and log of 1 is 0. So anytime you have a buffer with equal molarities of base and acid, the pH of that buffer is always going to be equal to the pKa of the acid in the buffer, because that part of the equation always goes to 0. Let's do another problem. Calculate the change in pH that occurs when we add sodium hydroxide to a buffer compared to the pH change when we add the same amount of sodium hydroxide to water. All right, well, let's start by finding the pH change when we add the sodium hydroxide to the buffer. So there's a lot going on here. Let's list our major species. Well, we have our buffer components, which is this acetic acid, and the base component of the buffer, sodium acetate, is soluble, so we'll have the ions. Of course, we have water. And then we're adding sodium hydroxide, which is going to dissociate into Na plus and OH minus. Now I already have sodium in my list, so I'm just going to add OH minus hydroxide. All right, these are our major species. Now, anytime you have a pure hydrogen ion or a pure hydroxide ion, if there's anything for it to react with, it's going to react to completion. So this hydroxide ion, it's a strong base. It's going to react to completion with any acid in the mixture, and we do have an acid. So what we have to figure is that these two that I just underlined are going to react to completion, and then there's going to be some sort of equilibrium that takes place after that. So we need to do stoichiometry first, and then equilibrium. So we're going to be doing stoichiometry with the acetic acid and the hydroxide, and a good way to start that is by figuring out how many moles you have of the solution. So let's find our moles of acetic acid. Now we have a 1 liter solution that's 0.5 molar acetic acid, so the molarity times the volume in liters is equal to the moles. So we know that that buffer is going to contain half a mole of acetic acid. All right, and we also are adding 0.01 moles of solid sodium hydroxide. And since NaOH has 1 hydroxide in it, the moles of sodium hydroxide is going to be equal to the moles of hydroxide. So if we add 0.01 moles of sodium hydroxide, we're adding 0.01 moles of hydroxide. So we need to figure out what's the stoichiometry involved when we have this reaction taking place. Half a mole of sodium acetates reacts with 0.01 moles of hydroxide. So let's figure out the balanced reaction here. We have our acid reacts with the hydroxide ion, and the acid is going to lose a hydrogen, and that hydrogen is going to be accepted by the base hydroxide, so we're going to be left with the ion of the acid minus the H plus and water. Now you can do traditional stoichiometry here. It's a limiting reactant problem, or you can do a BCA table. I like doing BCA tables for acid-base problems. And this is like an ice table, but instead of molarities, you put moles in. And we figured out we have half a mole of acid, 0.01 moles of hydroxide, and we will have nothing initially of the acetate ion. Oh no, that's not true. Initially, in the acetate ion, we actually have something here, because in our solution, we had that acetate ion. It came from the sodium acetate. We had 0.5 milliliters of 1 liter that contains sodium acetate. So it's actually the same calculation we did for acetic acid, because it's the same molarity and the same volume. But that's just because it's the same in this problem. It's not always necessarily the same. But we can just go ahead and find that initial concentration of acetate, because it does make a difference here. We've got 0.5 molar times 1 liter gives us 0.5 moles, and that's of sodium acetate. but since there's one acetate in that, that's also going to be equal to our initial moles of C2H3O2 minus acetate ion. All right, so initially we have 0.5 moles of acetate as well from our buffer. And we can ignore the water because it's not going to be part of our equilibrium. All right, so this is stoichiometry. Limiting reactant, it's a 1-to-1 mole ratio, so the smallest moles at the start is going to be our limiting reactant. So we're going to change by 0.01 moles, decreasing on the left and increasing on the right. So at the end, after this sodium hydroxide has reacted, we're going to have 0.49 moles of acetic acid, no hydroxide that would be hanging out because it's all going to react with the acid, and a little bit extra acetate ion. So what we can observe here is that when we added that base, it just took some of our acid in our buffer and changed it to the conjugate base in the buffer. So we started off with equal molarities of weak acid and its conjugate base, but after we added some base to it, we have a little less acid and a little more base. But instead of having strong base, we have a weak base because the hydroxide all reacted away. All right. Now we have an equilibrium situation because we have a solution that has 0.49 moles of an acid and 0.51 moles of a base, and we want to find the pH of that because we're trying to find the change in pH, knowing that it originally was 4.74. That was the original buffer. So we could do an ice table, but since we have a buffer, it's a lot easier to just use the Henderson-Hasselbalch equation. The pH of a buffer is equal to the pKa of the acid in the buffer plus the log of the base molarity divided by the acid molarity. All right, so the pKa is equal to negative log of the Ka of the acid. And our acid is HC2H3O2, and that's its Ka, so the negative log of that is the pKa. And for the molarities of the base and acid, well, we know the moles of base and acid, and we also know that we had a 1 liter solution, so the moles per liter is equal to the molarity. So our base is 0.51 moles in 1 liter, which is 0.51 moles, molarity, and 0.49 moles in 1 liter is the molarity of our acid. All right, so if we plug that all in, we're going to get the pH of our mixture, which is 4.76. All right, so our buffer started off with a pH of 4.74, and when we added 0.01 moles of sodium hydroxide, the pH became 4.76. So the change in pH is only 0.02, which is a teeny change, but that's the whole thing about buffers, is that they resist change to pH. But let's see how significant this is. How does that compare to if we just had water and we added the same amount of sodium hydroxide to the water? Well, for water plus sodium hydroxide, our major species would be the sodium hydroxide dissociated and the water. So when we add that sodium hydroxide, it doesn't really have anything to react with. There's no acid in this mixture, so we're just going to keep that OH concentration. So basically we're just having a dilute sodium hydroxide solution. So we just need to find the molarity of hydroxide and use that to find the pOH and the pH. So we have 1 liter of water with 0.01 moles of sodium hydroxide in it. So basically we have 0.01 moles of hydroxide in 1 liter of solution, because we're assuming that adding this solid is not really affecting the volume. So we have 0.01 molar hydroxide ions because we just put some hydroxide in water. So we can find the pH of that solution. We're not going to use Henderson-Hasselbalch here because it's not a buffer. We just have a base. There's no buffer. Has to be a weak acid and its conjugate base, or a weak base and its conjugate acid, but this is a strong base, so it's not a buffer. The pOH is negative log 0.01, which is equal to 2. So the pH is 14 minus the pOH, so the pH is 12. Okay. pH is 12. And we have to think, how much did the pH change? So it didn't explicitly state it in the problem, but we know that water starts out as a pH of 7. So if we had a pH of 12, changing from the initial pH of 7, that means the pH change was 5. All right, so let's think about this. We have two solutions that are 1 liter. We have two 1-liter bottles. One of them has a buffer in it, one of them has pure water in it. For the buffer, when we add 0.01 moles of sodium hydroxide, the pH does go up, but only by 0.02. When we have our container of water and we add the same amount of sodium hydroxide, the pH goes up by 5. So does that make sense? Yes, it does, because buffers resist change in pH. Why did the buffer resist change in pH? It's because it has this reaction. When we added the hydroxide to water, nothing happened. We just had the hydroxide, that strong base just sitting there. But when we had a buffer, when we added the hydroxide, it changed the acid, the weak acid, into weak base, so we ended up with a little bit extra weak base instead of strong base. So weak bases affect the pH less than a strong base. So buffers resist change to pH because if you add a strong acid or a strong base, it's always going to have something weak to react with and form instead of having a strong acid or base just sitting there. All right. Last question. Calculate the pH of a buffer solution prepared by dissolving 21.46 grams of benzoic acid and 37.68 grams of sodium benzoate in 200 milliliters of solution. All right, so it's a buffer because we have benzoic acid and its which is a weak acid, and we have its conjugate base, benzoate. So we have a weak acid and its conjugate base. So since it's a buffer, we can find the pH by using the Henderson-Hasselbalch equation. And we need to find the pKa and the molarities of the base and the acid, but then we should be good to go. So the pKa is the negative log of the Ka, and the Ka of our acid is not given, but I looked it up, and it is 6.4 times 10 to the negative 5th. That's the Ka of benzoic acid, so the negative log of that is going to be equal to our pKa. That's 4.19. And then we can find our molarity of our base. So our base is sodium benzoate, 37.68 grams. We need to find out our moles per liter of that. So sodium benzoate is NaC7H5O2. And if we want to find the grams and convert that to molarity, we need to figure out how many moles it is and then divide by liters. So we have to find the molar mass. So we have the 1 sodium, we have 7 carbons, we have 5 hydrogens, we have 2 oxygens. So we get a molar mass of 144.1. So if we have 37.68 grams of that stuff, and we know that 144.1 grams is 1 mole, then we've got 0.261 moles of sodium benzoate, and it was in a 200 milliliter solution. So our molarity is going to be the moles per liter. So don't forget to convert milliliters to liters. So anyway, the molarity of our sodium benzoate is 1.31 molar. And we also, so we were just chugging away at our Henderson-Hasselbalch equation. We've got our pKa, it's 4.19. We have our molarity of our base, it's 1.31. You need to find that molarity of the acid. So we have 21.46 grams of the acid in that same 200 milliliter solution. So let's find the molar mass of our acid. So we have 6 hydrogens, 7 carbons, 2 oxygens. So that adds up to 122.13 is our molar mass. We had 21.46 grams of this one. So we can convert that to moles. We've got 0.176 moles of our acid. I want to find the molarity. It's the moles per liter. Same 200 milliliter solution, so that's 0.2 liters. So that's 0.879 molar of our acid. All right, so now we have all the components of our Henderson-Hasselbalch equation. Our pH is equal to our pKa plus log base over acid. So our pKa was 4.19. Our molarity of our base, that was our sodium benzoate, it's 1.31 molar. And then our molarity of our acid is 0.879. So our pH of this buffered solution is equal to 4.37. And that's not too far from our pKa, 4.19. So that's a reasonable answer.